Thanks, Chairman, for introduction. I'm Tatsuhiko Ikeda from Riken, Japan, but I'm temporarily in Boston University. And today I'm going to talk about quantum states under Floquet heating. This talk is based on these two recent papers. And my collaborator is Anatoli, Polkovnikov, and Sho Sugiura. And Floquet theory and experiment in many-body systems. In this talk, I'm going to focus on isolated systems, the Schrödinger equation with the periodic Hamiltonian, and a capital T plays a role of time periodicity. And as all of you know, Floquet engineering concept has attracted much attention recently. The idea here is that by introducing some time periodic external driving, we can map it through Floquet theory to obtain a time-independent effective Hamiltonian. And by irradiating the circularly polarized light onto the graphene, we're going to get as effectively a time-independent Hamiltonian, which is a Holden model of the topological insulator. This kind of theoretical proposal has been realized in cold atom experiments using a shaken optical lattice. There are a huge number of theoretical proposals and many experimental studies are going on, but I cannot list all of them in this figure, but the concept is the engineering by periodic drive. So what is the effective Hamiltonian? Since this is the core concept throughout this talk, I'm going to review this more carefully. For example, we consider a switching periodic drive between H1 and H2 like this. We're going to get a single cycle unitary like this between H1 and H2. And then this U is a unitary matrix. There always be a Hermitian matrix, which is HFEX. This is what we call exact effective Hamiltonian. And because this reproduces the stroboscopic evolution exactly, but this is exact, but very complex in the sense that it is non-local in general. On the other hand, we can introduce the effective Hamiltonian approximately without any superscript EX here, FEX. What is this? So U is defined like this, and we consider the case where T is small, short period, or correspondingly, this is the high frequency regime. In this case, using the BCH expansion, we're going to get some HF, which is given by a series expansion in terms of T, T squared, T4, T6, etc. And according to this kind of seminal or mathematical theory, this kind of high frequency expansion or short period expansion is known to be asymptotic. So it's not convergent in the thermodynamic limit. So we have to terminate at some point of this series. That's why we call it approximate, because the termination introduces some error in here. But this HF, effective Hamiltonian, is quite useful because it's local. As you can see, it consists of commutators between Hamiltonians. If each of these are local, then the commutator will also be local. So this approximate Hamiltonian is more useful, and it is a guide for engineering Hamiltonians. The physical consequence between the difference between the HF and the HFEX is the so-called Floquet heating. This is the schematic illustration of this heating. So the red one illustrates the dynamics obeying the exact unitary dynamics derived by the HFEX. On the other hand, we can plot the effective approximate dynamics due to HF based on effective Hamiltonian, which is something like this. So in the early stage, these two dynamics are quite similar because the Hamiltonians are similar and the time is short. But as time goes on, the small mistake will accumulate up to a huge effect. And for the exact dynamics, we're going to get some heating to the infinite temperature with zero energy expectation value like this. On the other hand, for the approximate Hamiltonian dynamics, we don't see any heating. This is because the HF plays a role of the energy conservation. This is a local Hamiltonian, and in the time-independent case, so there is a conservation law for HF, so we don't have heating. If we plot x in a linear scale, we're going to have some slope in here, which is called the heating rate. It's an energy increase rate. And there are these seminal mathematical rigorous work that gave us an upper bound for the Floquet heating rate. So this is given by an exponential decay in terms of the driving frequency. So this is a very huge suppression of the upper bound. And here are some questions that we address in this talk. What are the quantum states after Floquet heating sets in? What are the states? This is the first question. And another question is, what is the way to calculate the real heating rate rather than the upper bound? And our short answers are the following. The first one is the thermal state in terms of the effective Hamiltonian, where the temperature is time dependent and it gradually increases as the time goes on. And the second answer is yes, by using something like Fermi's golden rule, which I will explain. By using this, we can calculate the heating rate quantitatively. Before moving into our original study, we're going to briefly review the previous study about the bare FGR for small amplitude drives. In this study, they assume that the Hamiltonian consists of H0, this is the time average part, and plus some perturbation, which is periodic. The assumption is that the perturbation is weak, the amplitude is small, and H0 is non-integrable. These are key assumptions. Since this is a conventional setup, we can resort to the time-dependent perturbation theory and utilize the Fermi's golden rule to get energy increase rate by these formula. And also, H0 is non-integrable, and it's reasonable to assume that each state is assumed to be thermal using a single parameter beta of t like this. Now we have a couple of equations for the time-dependent temperature and the energy increase rate. So we can solve these couple of equations self-consistent way. Then we are going to get some time evolution of the energy. Then it was shown that this time evolution dynamics will reproduce the actual heating dynamics. And so remaining issues are obviously, what about the large amplitude? What is the case where so this is kind of crucially important case in the Floquet engineering viewpoint, because for the large amplitude case, we can make effective Hamiltonian that is significantly different from the time average Hamiltonian. So we can make some non-trivial thing. But the difficulty is that the driving plays two roles. The first role is to dress the Hamiltonian from H0 to H effective, and the second role is heating. So how to deal with these two effects separately is a key question in this work. Oh, no, actually, we don't really do system bus decoupling thing. What we rely on is the eigenstate thermalization hypothesis. So real system is pure, but we can reasonably approximate it to be mixed state like this, as long as each eigenstate is thermal. That is an excellent question, and as far as I know, there is no such work yet, so you can do it. And so, okay, what about the large amplitude case? So this is our outline of results. So we developed, we generalized this scheme for large amplitude or strong drive regime as long as the frequency is high. And we named it as a Floquet version of FGR, so Floquet FGR. And we can prove that this FGR reduces to the previous or conventional one in the weak amplitude limit. So this is a sketch of our result. By changing the driving amplitude, we're going to get these dots of heating rays like this. It shows a non-monotonic behavior, which is obviously non-perturbative because, according to the perturbation theory, we can get just a monotonic behavior. We can reproduce this non-monotonic behavior in the strong drive regime, which I will explain in detail below. So our Floquet FGR. So we start with the effective Hamiltonian, which is assumed to be obtained by some high frequency expansion terminated at some order. We're going to show that by increasing the order of approximation, we're going to get better and better results. And the state ansatz is a generalization using this HF. So our state is assumed to be diagonal in the eigenbasis for this H effective. And we also introduce the assumption that this is non-integrable, and we assume that each eigenstate population obey the Boltzmann weight with introducing only single parameter beta t. And now we can get a master equation among the eigenstate population, P of M and N. And here, the transition rate, W, M to N, is given by this very simple formula. The matrix element between N and M for the delta U operator, which is a small mistake of a single unitary, single cycle unitary, U and a U effective dagger, which is assumed to be small. And the second contribution is a delta function, which means the energy matching condition, including the driving frequency. So it's a kind of resonance condition for the drive. And now we have a couple of equations for the effective temperature and the effective energy expectation value and its increasing rate. We can solve them a self-consistent way to get some curve for the energy increase. And now we're gonna check this scheme for some concrete model in a spin chain. We're gonna use the L-size spin chain with a periodic boundary condition. We assume that our initial state is the thermal pure state at a non-zero temperature. And we evolve it using a Kirchhoff evolution method. And our Hamiltonian is a switching between H1 and H2. And its average is 0, and the driving is plus V and minus V. And V is a Zeeman field along the x-axis, while H0 is some non-ergodic thing. So the solid curves are the energy expectation values dynamics in the Floquet cycle. And different color from blue to pink corresponds to the different system size from 12 to 20. And obviously there is a big finite size effect manifested as a heating saturation, which becomes smaller and smaller as we go to larger system sizes. And so this is the exact evolution for Floquet dynamics. Initial state is some finite temperature thermal pure state. With respect to H0. And on the other hand, we can implement the Baire and the Floquet FGRs to draw the energy increase curve. And as expected, Baire and the Floquet FGR overlap almost perfectly because we are working now on a small amplitude drive for which we prove that our method reduces to the previous one. And both of these are working well. And nicely, we plotted two different system sizes, L equal to 14 and 16, and we get the same result. This means that this FGR shows a very nice quick convergence in terms of system size. So by only with 14 sites, we can extract the information about the thermodynamic limit, even though the actual dynamics is still suffering from the finite size effect. So this shows some practical advantage for simulating the heating dynamics. Mm-hmm. Actually, we introduce it in every step of evolution. So at some point, we can get some energy increase. Then we know the next step temperature. Then we, yeah, so. And now we, no, actually we picked a single one. And it works well for larger system sizes, thanks to typicality. Sorry, 600. Oh, this is my personal limitation. So I fixed it. I mean, you want to know the fourth order, second order? Oh. Yeah, honestly, I don't know. So this is what I could do. Right, and as you know, as written in your review, there is some optimal order in the Magnus expansion. So that would be ideal case, I believe. But in numerics, we cannot go that far. So yeah, conceptually, that optimal thing would be the best. Is that fine? And so now we increase the amplitude in the non-perturbative regime up to 3.0. Now, yeah, we can repeat the same thing for solid curves. And now it's beyond the perturbative regime, so the bare FGR doesn't work well, whereas our Floquet FGR works better like this. So it's nice, and also nicely, again, it shows a nice size convergence. We can know the thermodynamic limit in the L equal to 14. And yeah, it's related to the question. So we still see some discrepancy between the real and our calculation. And I expect that this reason is the insufficiency of this HF, but so the result depends on the order of HF, as we will see in the next slide too. So finally, we mentioned the importance of the difference between the HF and H0, and it's manifested as a non-monotonic heating rate. Oh, in my terminology, it's just defined by the amplitude strength. So in both regimes. Yeah, yeah. Yeah, so for your sense, the true strong driving is still an open question, whether there is such kind of nice H effective exists or not is still an open question, I think. So yeah, we're both limited to the high frequency regime. And now we compare different heating dynamics for different amplitudes from 0.25 to 3.25, from dark to blue to light. And we get increase of the heating rate as a function of amplitude. If we go beyond from 3.5 to 6.25, we rather in turn get a decrease of the heating rate. So this is some clear manifestation of non-perturbative effect, which was reported by Arnab and Asmi already. But the nice thing is we can reproduce this non-trivial, non-monotonic behavior using Floquet FGR. So this is the plot that we saw before as a function of driving amplitude and driving heating rate, and we're gonna get some dots of data like this as extracted from those upper panels. And as you can see, for the bare FGR, we're gonna get a monotonic increase as a function of HX, like quadratic. But a Floquet FGR for the lowest and second order, fourth order, sixth order results, and we finally get reproducing the non-monotonic behavior like this. And as you asked, in the real high amplitude regime here, is not reachable in this approach. This is an open question. This regime is where the BCH series breaks down because the ratio between the HX divided by omega becomes larger, and this kind of high frequency expansion breaks down. And maybe there may be some approaches needed, and you can see this paper by Takashi Mori. He's unfortunately not here in this week, and he develops a non-FGR approach to the same issue about the heating rate, so you can check this out. Mm-hmm. Yet there is a huge discrepancy between the solid blue line and the conventional line. Oh, it converges the same thing around here. So it's debatable to discuss and h equal to 1. You're saying that anything, all the values of hx larger than 1 are already well beyond the bare GR. Yeah, in this sense. Yeah. So let's summarize my part 1, even though I spent most of the time. And, okay, and so our question was, what is the quantum state after heating sets in? Our short answer is a thermal ensemble with a time-dependent temperature. And the increase of the temperature is determined by the increase of energy or heating, which is given by a master equation called Floquet FGR. This conclusion is something useful for the Floquet engineering perspective, because the HF engineered Floquet way still meaningful after heating sets in. So the Hamiltonian itself survives, but what changes the temperature? So we can talk about a Hamiltonian, effective Hamiltonian, even after the heating sets in. So there are some remaining questions, but some of them are pointed out by some audience, so I'm not going into detail. So now, let's continue our discussion of Floquet heating in another way. And in the previous work, we assumed that our initial state is non-zero temperature, or well above the 0 temperature. And also we secretly waited for 10 cycles before we compare the FGR. So what happens here is there's some relaxation of the quantum state. And we encountered some discrepancy between the Floquet FGR, between the real dynamics, or if the initial temperature is 0. So initial state is 0, initial temperature is 0, case is somewhat special. So it's still open. So I need to look into detail about this story about the ground state in the next part. So here's related work by Marcus Heil and co-workers in the context of totalization. Yes. And totalization is a kind of Floquet systems because it's a switching of Hamiltonians between 2 or 3, like this. And if we torotorize the transverse and longitudinal field Ising model, then we're going to get that H1 and H2 like this. The one specialty is that H1 and H2 contains only mutually commuting terms, like Z-like terms and X-like term. This is a special case of Floquet thing. And they took one single initial state, which is all up, and they studied the dynamics of magnetization in the Z direction. And they plotted the long time average of magnetization against the Trotter time step, or in the Floquet language, this is the time period or the driving period. In the short period regime, they saw a nice quadratic dependence at some point. It suddenly drops to 0 value, which is corresponding to the infinite temperature state in the Floquet language. So they saw some transition-like behavior, which is called a Trotter transition. But it was surprising to me because I believe the Floquet ETH for generic non-integrable setup like this. So according to this, every state will eventually heat it up to the infinite temperature state. This does not allow this kind of smooth behavior at some finite frequency. So I guess there is some initial state dependence of heating. And this could be true because old up state is kind of special because H1 has many terms, but each of which is minimized by this old up state. So this old up state is very cold. So this suggests that some ground state plays some special role. So in the previously, aside from the trotterization argument, in the Floquet community, some transition-like behavior in terms of tau was reported and studied. But as far as I know, such kind of initial state dependence wasn't studied very much. So the method, it's a real-time evolution of this dynamics using a quantum circulate simulator. So the specialty of the trotterized dynamics is that each of which is represented by a local unitary gate. So our task is to apply these unitary onto our initial state as efficiently as possible. This kind of optimization has been done in the quantum computation community. So we can borrow their packages, and now we can go beyond L equal to 20 or something within a realistic time scale. And our measure of the robustness of the initial state is the fidelity like this. And this typically decays exponentially with this L. So we normalized like this in a thermodynamic sense. We expect some order 1 quantity for this. So now, using this trotterized structure and circulate simulator, we can go to the L equal to 30 to get this kind of dynamics. Different color corresponds to different tau for longer period to shorter period. And it shows some continuous dependence, but suddenly it goes to no heating. So here is, we see some discontinuous dependence in T. And now to look into more carefully the dependence on tau, we introduce the time average of the fidelity. And the sigma is the Gaussian cutoff for the time scale, the long time cutoff. And we introduce the normalized version as well. This is a plot for the time averaged normalized fidelity versus tau. And here is some special threshold value below which the time averaged fidelity only changes smoothly, and above which it goes to large value. And here the color corresponds to different cutoff, and from blue to pink we have 100 cycles to 10,000 cycles. And now we focus on the ground state of, I forgot to mention, so our system size is 24, and our initial state is the ground state of the time average Hamiltonian, or the lowest order effective Hamiltonian. And now we can switch to the ground state of the second order effective Hamiltonian, for which we get the same transition point, and below which we get a flatter dependence of time average fidelity, and we still see some jump like this. And on the other hand, we can fix sigma, or the time scale, and then we can change the system sizes like 18 to 30. We don't see any move of the transition point, which is suggests some transition. And we conjecture that this kind of real discontinuity happens in the thermodynamic limit, but the key is to take the infinite size limit first, and then take the infinite time limit to avoid the heating saturation as a finite size effect, which we saw in the previous part. That sounds pretty intriguing. So let's chat about it later. Please, yeah, we have 4 more days. Okay, yeah, thank you. Thank you for your comment. And yeah, for now, we've been focusing on the ground state, and we'd like to confirm that ground state is actually special. And now we're gonna check other states as well. And we took all the initial eigenstates in terms of the time average Hamiltonian, and each point corresponds to each eigenstate as an initial state, and the y-axis shows the time average, the fidelity. And the ground state lies in the leftmost part, and each different color corresponds to different system sizes. And the ground state is so special that we don't see any L dependence if normalized. On the other hand, for most states, we have a strong size dependence to go to the infinite temperature state. So we see that the ground state is so special. By the way, this is tau equal to 0.5 below the transition. So if we increase the tau to 1.2 above the transition, we finally get the L dependence, or the increase of the ground state as well. So it's, yeah, like this. And one remark is that here is also a highest excited state that shows the same property like GS, but we don't care because it's kind of a ground state. If we redefine the H to minus H, then this guy comes to the ground state. So I would claim that both edges of the state are so special. And finally, I'm going to talk about, yep. Mm-hmm. Yeah, that is an excellent question. So for this, we fix this one single order. And for the fixed order, we see this kind of behavior. And for the zeroth order, second order, each of which. And finally, I mentioned that this transition point is beyond the convergence radius of the high frequency expansion. And to see this, we obtain an exact eigenstates of single cycle unitary like this. And then we can get a plot like this called a spaghetti plot by some person. And for each point corresponds to an eigenstate. The y-axis, the theta alpha, which is the eigenvalue, like this. And for the short period regime, so this high frequency expansion works. So we can use this HF, and our theta are the product of En tau. That's why we see some linear structure here. And in the lowest branch corresponds to the ground state of the Hamiltonian. Then if it touches the minus pi, it reappears from this top due to the modulo 2 pi structure of the Floquet eigenvalue. And this is the scale of the 1 over L because each energy eigenvalue is extensive. And this is related to the convergence radius of the high frequency expansion, and above which technically this expansion breaks down. But as we saw, the transition point is order 1, like 1.2, which doesn't move as a function of L. So this is beyond this scale. What happens is that there is this ground state branch penetrates into the continuum states, even though it is stable. It goes to here, and then it's mixed up and disappears. The thing is, the ground state of effective Hamiltonian has a large overlap with these scar-like states. That's why we saw some robustness below this transition point. So to summarize the part 2, so we use the circuit model and the simulator. We numerically study the Floquet heating up to the L equal to 30. So unlike the most states, the Floquet effective ground state is very robust against heating and exhibits a non-monotonic behavior or a transition-like behavior as a function of driving frequency. It is kind of a counterexample to the strong Floquet ETH because it offers some non-heating state. So there are a couple of remaining questions. And this is the ground summary. I talk about the quantum states after the heating, and the HF is not just an approximation for the early stage of the thing. It still tells us something about the later time dynamics. So the roles are shown by these two works, and thank you for listening.
I'm trying to figure out, again, what of this is inherently quantum. The Trotter transition, one would expect that should exist classically, no? Just take spins that are spins J for large J, your same chain, it's a purely classical system. Why wouldn't it have a transition?
I don't know an example of the Trotter transition in the class.
Did anybody try?
Oh, it's a strong statement. And as far as I know. Oh, yeah.
And the reason for this is that you don't need to solve the equations of motion using an ODE solver if you do this stepwise drive. And this is actually important because you need to go to very long times and you need to make sure that you don't accumulate any error in the evolution. And the behavior of the classical system is very similar to the behavior of the quantum system. Yeah. So in that sense, Floquet heating, there's not much quantum in it.
Oh, yeah. Did you find some transition in that model?
We did not find like a proper transition. Yeah. So if this is a proper transition, then that would be like a proper difference. But what's different, for instance, in a quantum system compared to a classical system is that quantum systems might have gaps, whereas classical systems always have continuous spectra. And so you can imagine that if, like this is like a feature due to like some discrete energy spacing that could not occur classically.
You also have these, these lines later, larger values of tau. Is there anything special about those?
Actually, I think this is not an exact scar, like in your model, your scar is protected by symmetry, right?
Right.
But there is no such symmetry protection in here. Actually, we have some very small, tiny level repulsion between other states, but look at this. So this is a very, very tiny level repulsion. Okay. So this happens because the smallness of the coupling between this state and this state. These are macroscopically different, and their matrix elements is as small as 1 over square root of D, which is, expected by off-diagonal ETH and something. Okay. So this smallness, it leads to this small gap.
Thank you. Any other questions? Yeah, go ahead.
So yes, that is true. That's why I talk about the one order of two limits. So first we take L to infinity first, then take the longer time limit. If we take in the opposite way, you're gonna suffer from this thing. But I believe that this kind of thing becomes smaller and smaller as we go to larger system sizes.
And you've seen that in the data?
Oh, not actually. I mean, it's hard to follow this crossing because as we change different system size, and yeah, I mean, it's quite difficult to follow each of which in difference.
I actually have one question about this plot where you showed the energy density dependence on the x-axis. Can you go back to that slide? So from there, it looks like there's something like a mobility edge, if I can call it, or at least not this one, the one on the next slide. Here, yeah, exactly, the left plot. So it looks like there's some critical energy density, and then below that critical energy density, you don't heat up, and above it, you heat up very much. So have you looked into states that are close to the ground state? So the first few excited states, it looks like they behave in a similar way.
Yeah, I don't have an idea yet. So yeah, I'd like to chat about this later because it's how many robust states are there. It's very difficult to answer, so I couldn't. So please discuss the way. Thank you.
Okay, so if there are no other questions, let's thank Tatsuhiko for a very interesting talk.